So what we got today is we're going to look at a few more different types of graphs and displays that we can use for various data types. Everything we looked at in section 1 was based on a frequency distribution. We don't need a frequency distribution to do these graphs. So in some ways they can be a little bit less time consuming, in other ways it can be a little more. It depends on the data set. The way the data is distributed and how it looks will make an impact on which displays are more efficient or better at showing trends and patterns and behaviors within the data. So that's something that you need to be aware of and kind of be paying attention to is, based on the numbers that we have, what's a better display of data? What's a better way to organize it? The first one we're going to look at is the stem and leaf plot, where data is separated into a stem and a leaf. The leaf is always going to be the ones digit. And in the stem, you can think of as very similar to our classes on a frequency distribution, but the stems are always grouped by counts of 10. So if I have a stem of 1, that's all the numbers in the teens. If I have a stem of 2, that's all the numbers in the 20s. A stem of 3 is all my numbers in the 30s, and that continues. If I go above 100, well, if I have a stem of 10, that's all in the 100s and 1s. A stem of 11 is 110, or the 100. So the stem is going to be based off of that base 10, while the leaf is always going to be the single digit, okay, the digit at the end. So when we have a set of data here, 50 cell phone users, the amount of text messages they sent in one day, display the data in a stem and leaf plot. So we want to look at what's the low value, what's the high, what's the minimum and the maximum. Just like with our frequency distribution, we first want to identify the minimum and maximum value because we need to know what stems we need. So we look through the data set and we see that we have a minimum value of 17 and a maximum value of 148. Okay? So I need stems that go through that whole entire range. Your leaves are all the singles digits, and then your stem is every other digit on the left. So for the number 75, my stem is a 7, my leaf is a 5. For 49, stem is 4, leaf is 9. For 104, the stem is 10, and the leaf is 4. So if I'm starting with a low of 17, I need to start with a stem of 1, and then a high of 148, I need to end with a stem of 14. So I need to list the numbers 1 through 14 all the way down next to a vertical line. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? So those are all of our stems. Then we want to go through the list and we need to fill out all of these. So we're going to start with any number that's in the teens that has a stem of 1. So we go through our list and we check to see any of these numbers that have a stem of 1. I've got a 17, I've got an 18. No other numbers have a stem of 1, so those are the only 2 numbers in that row. And then we just write them in order. So I have a leaf of 8, and a leaf of 7, and a leaf of 8. So that row displays 2 data points, 17 and 18. Cross those out. Then we go to the next stem, which is a 2. So we go through our list and we look to see, okay, do I have any numbers in each of these rows that have a stem of 2? All right, I don't think I missed any stems of 2. And then we look and we start with the lowest number. What's the lowest number that has a stem of 2? 20. So we start with a 0. Okay, what's the next lowest number that has a stem of 2? 23. And after that? after that, 5. And I have 3 of those. So I need to list the 5 3 times. Okay, after that, 6. And after that, and after that, and after that, it's the ones place. Or the stem is the not ones place, the leaf is the ones. Okay, so the second row lists all the numbers in the 20s. 20, 23, 24, 3 25s, 26, 27, and 2 29s. Do the same thing, fill out the rest. These are the stems. So because our highest number is 148, we need to go all the way down to 140s. That's why we go down to 14. Okay, so this is the 10s, 20s, 30s, 40s, all the way down to 140s. Okay, so once we've got all of our leads in, we can do the same thing that we did with histograms, and we can describe patterns. We have a visual display of how the data is grouped and organized, so we can describe any patterns or trends that we see. So what do we notice? Okay, so there's only 113. Do I have any values in that with that stem? Is there anything that has a stem of 13? No. So there's no values in that class. So we have a minimum value or a minimum frequency. There's nothing in the class 130. Okay. What else? Okay, so with the stem of 2, so in the 20s, okay, that's where we have our highest frequency. What else? What else? Yeah. Most of our values are in that lower range. So we see that from 20 to 50, that's where a big bulk of our numbers are. We can visually see that there's just more numbers there. So the bulk of our data is in that lower end. As we get above 50, maybe even above 70, we see how it starts to kind of taper off a little bit, and there's fewer data values on the higher end. Okay? So again, those patterns that we're describing, what area has the most? Where's the least? Is there anything that is unusual or outstanding with any of those values? Okay? Are any of those values kind of far away from everything else? Anything on any of these data values unusual compared to the rest? Why do you say the first one? So remember that these are, so there's only 2 in the first one, right? But this is, so the data point 17 and 18. Still pretty close to 20. 17 is not far from 20 or 23 or 25. 148. You could probably consider that an unusual data value. Pretty far from the bulk of it. And you have those friends that like send like 5 messages in a row, just like really quick bursts.
Correct.
Good. Okay. So, looking for unusual data values, anything that's far away from the rest. Okay, all of those are patterns that we can look for in the visual display. Benefits of a stem and leaf plot. We get that same kind of trend that we do with a histogram where we can visually see what groupings are the most, which groupings are the least. But it preserves the individual data values. So as a histogram, I just have the bars. I don't know how many numbers are in each of those ranges. With a stem and leaf, I still have the numbers. So I know how many are 20, 23, 25, 29. I know how many data values are in each of those specific things. Okay? Downside, can take up a lot of space, depending on your data. Okay? So it could be more of a writing commitment, having to make sure you have enough room to fit all the values, depending on how long your list is for your stems and how long the list for some of your leaves can be. So it just varies whether or not it's useful. Another display is a dot plot. If you take a stem and leaf plot and just kind of turn it sideways, it's going to resemble a little bit like a dot plot, but instead of numbers, we have dots to represent each of those numbers. We plot every data point on just a horizontal axis, but notice instead of grouping it by stems, every single number is listed. So we still get a visual display of grouping our data, but a downside is we have to include every single number between our minimum and our maximum value. So when we look at plotting it, I've included a number line here, and I've just broken it up by 5s, just so that we could fit everything. Because I have to go all the way from 17 up to 148. So I have to be able to plot each of those points. And I'm just going to use, I've got the stem and leaf plot, so I'm just going to use those numbers since they're already in order. And I'm going to use those to plot these dots. Okay? So we start with a 17 and an 18. Then we have a 20 and a 23. And then we have 3 25. So we're going to plot 3 dots up on the 25. 26, 27, 28, a little bit more room, 27, 28, no 28, sorry, 29s here, 2 30s, 32, 33, 35, 36, 38, 40, 1, 2, 3, 6, 9, 2 of those, 52, 54, 55, 59, 66, 68, 69, 73, 75, 6, 8, 80, 81, 4, 8, 98, 104. Ladies, please stop whispering. If you have a question, feel free to ask it. Otherwise, be quiet. And 148. Okay? This data set, not ideal for a dot plot. Why? Why is it, what about it is making it tedious? So the number of dots, not that big of an issue. It's a little bit more work. Not specifically the number of dots. Someone said something else.
The accuracy.
Why is the accuracy getting difficult?
Because you don't know exactly if you're like.
Say that again.
It's so spread out.
It's so spread out. The range is huge. So when we have a large range, dot plots aren't going to work as well. They'll still work. And now we also have various software that will do all of these displays for us, so they can still be useful. But when we have this large range, dot plots become less useful because everything's so spread out. I can still get information. We can still see the same trends. Hey, most of my data is kind of in this range, okay? In that area, that's where a lot of my stuff is grouped together. We see that as we get above 50 or 85, well, our dots start to spread out more, and we have fewer and fewer data entries. So we can still see that visual trend, but because it's on such a large range of numbers, its effectiveness gets less. And so grouping it with a stem and leaf gives us that same general information, but in a much more compact way. If my data set had a smaller range, dot plot could be great because it preserves that individual value. I can look at which specific numbers have more frequency more easily. But that long range, less useful. The example here, we have a smaller range of only 25, much more manageable, and we can quickly see the numbers 25 and 36 have our highest frequency. We have a big gap in the 30s and the 40s. Okay, we can see that visually much better with a smaller range of data. Even if I added in more data values to my dot plot because I have a larger set of data. Okay, even if I have more dots, yeah, it's going to take more time, I have more data, but it still allows me a quick way to look at specific values versus the stem and leaf, which lets me quickly look at groups of values. Okay, so two different ways to kind of display. And again, it's going to vary based on the needs as well as how your data is distributed. Now, both of those data sets were quantitative. They were numerical data values. Not all of our data is quantitative. Some of it is qualitative. Well, you can't graph college degrees on a number line because there's no number associated with it. So we have to have other ways to describe that information. That's qualitative. Very, very common is our pie charts, pie graphs. Pie graphs use the area of a circle to indicate a percentage that that response or that data value consists of the whole. So we divide the circle into sectors that represent each category, and it will always be proportional to the frequency of the category. If half my data is in one category, then half of my circle will be shaded for that. If 20% is in a category, then 20% will be shaded. So our new graph here that we're going to do is the number of degrees conferred in thousands in 2019. Given the table, we want to take that and organize it into a circle chart. The process will be that you need to multiply the relative frequency by 360. Okay, so for each category, we'll find the relative frequency. That gives us a percentage. And then we multiply that by 360. That tells us the angle that we'll have inside the circle. Remind me how I calculate relative frequency. Yep. Frequency divided by sample size. All right. So we'll start with our associate degree. All right. We need our sample size. How do I get my sample size from that table? How do I get my sample size? But we just need to do the first part. We just need to add up all the numbers. Okay. So our relative frequency for the associate's degree, start at 1,034, divided by 4,072. What do we get? So we get 25%. So the associate's degree consists of 25% of my sample. We want to take that 25%, multiply it by 360, and that gives me the angle measurement. 25% of 360. 90 degrees. 90 degrees. So from our central angle, from the center, we have a 90-degree angle, and that's going to be our associate's degree, which accounts for 25% of our sample. Okay? All right, same thing for bachelor's. Frequency divided by the sample, 490. Times it by 360. 170 what? Yeah. So almost 180. So we have a straight line, just a little bit less, not by much. And there's our bachelor's degree. And that accounts for 49%. Masters. Is it 20 or 21.204? Okay. And then what's our degree going to be? 70 what? 72. Okay. So for the section we have left, that's going to be this corner. So can't get it exact, but it's going to be the majority of what's left. That's our master's degree. That accounts for 20%. And everything we have left is just going to be our doctoral degree. 188 divided by 4072. We get 0.05. So what's left is going to be our doctoral at 5%. Rounding, we're off by just a little bit. We're short by 1%. You have a question? We can, but that's my last category. That's the only wedge I got left. Can't be anything else. It ends up being 17%, or 17 degrees, 18 degrees. We've got our last category. Doctoral is going to be 5%. All right. Based on rounding, you see we're 1% short. So sometimes we'll be off by 1 above or below. Pay really close attention to rounding directions. On some of your questions from yesterday, it may have said round to the nearest hundredth, so that's the nearest whole percent. If it wants a part of a percent, then it may say nearest thousand. So just pay attention to any rounding directions that may take that into consideration. Pie charts, super common. We'll see them all the time. Pareto charts are nice because sometimes people like bars. They like to kind of see that relative height difference. The difference between a Pareto chart and a frequency distribution is that the categories are listed in order from greatest to least. They're always going to be listed in order from greatest to least because we don't have a number line, so we don't have to put it in numerical order. We're dealing with qualitative data. So Pareto chart just orders it from greatest to least, but everything else about it relative to a frequency histogram is very, very similar. Our horizontal axis is going to represent our categories, while our vertical axis represents the frequency for that category. So we have the leading causes of death in the United States. We have accidents at about 173,000. We have cancer at almost 600,000. We have lower respiratory disease at 156,000. We have heart disease at 660,000, and then that leaves us with strokes at 150,000. So we're going to order the data in a Pareto chart. We need to start with the highest frequency. What is our highest cause of death? Heart disease. So our first category is going to start with heart disease. Okay. What is our next leading cause of death? Cancer. After cancer? After accidents? Respiratory disease, lower respiratory disease, and then that leaves us with stroke. Step my graph just a little bit. All right. All of our numbers are in the hundreds of thousands, so we can set our scale based on that. We can use hundreds of thousands. So we can start with 100,000, 200,000, 300,000, 400,000, 500,000, 600,000, and 700,000. Okay, nothing above 700,000, so we can stop there. We want to label our axes as well. So our horizontal is our cause of death. Our vertical is the number of deaths in the thousands. So we want to make sure that we list the scale. If I didn't include thousands on that scale, then when I drew my bar for cancer, it would just be 600 people, not 600,000 people. So we need to make sure that the scale is properly labeled. Cause of death, and then death in thousands. So we start with heart disease. How many people died from heart disease? Approximately. Okay. Where would that put me on my graph? How far up am I going to go?
In between.
Yeah, in between the 6 and the 7. Just get it close. Doesn't have to be perfect. On a Pareto chart, unlike with the frequency distribution, we do not have to have the bars touching. Actually, we usually don't have the bars touching. So you'll have a little bit of a gap from bar to bar. All right? Where's our cancer going to be? Pretty much right at 600. Cancer. Where's our accidents going to go? A little bit under 200. Lower respiratory disease? Lower or higher than accidents? Just a little bit, not by much, right? Stroke? Pretty much right below that, right? Not much. Just right below lower respiratory disease. Okay? What patterns or trends do we see in the way that this data is displayed? Okay, what categories is that? What are those categories? So most of our deaths, by a lot, are heart disease and cancer. So we can see that the leading cause of death is heart disease. Cancer's not far behind. And then there's a big gap between the next leading cause of death. Huge gap between the second and the third leading cause of death. And then even our third, fourth, and fifth, is there a big difference between those? No. Okay? So most of our deaths in the first two categories, and then the rest of them significantly less, and not much difference between the three categories. And so our Pareto chart sets it up in a way for us to easily see the differences in the values, in the categories, from greatest to least. Okay? All right. We will stop there for today, and then we will finish up with our last